let's start with the chapter probability distribution. Now let's assume we have a particular data and it's a very large data, maybe 1000 or more points. Now whenever I need to find mean, standard deviation, variance, skewness or any kind of moment or do any kind of analysis, I have to use the whole data, all the 1000 points or more, to actually analyze or to come up with these values. Now it becomes very difficult as well as very lengthy work to do so. So what we have done is we have made some probability distributions, some generalized probability distributions using some formulas, and we have found that majority of our data will follow one of these probability distributions. And just by changing the parameters of these particular probability distributions, those parameters are constants, we can fit almost every kind of data into these few probability distributions. And then what we can do is we can do analysis on these probability distributions and not use our actual data to come up with these values as mean, variance and skewness and so on. So let's study this probability distribution. Now as our data is of two types, probability distribution is also of two types. First let's see discrete distributions. Among them, first we are going to study the uniform distribution. Now uniform distribution has a special characteristic. Every value in a uniform distribution has the same probability. That is why it is called as uniform. So we say probability of a particular value small x being this variable x is equal, or I can say 1 by n, where n is the number of terms. In this we can have many different values of uniform distribution of x, and each of them will have probability 1 by n, or 1 by divided by the total number of terms of those x, variable x. Now let's take an example. Let's assume that 1, 2, 3 till n. These are following uniform distribution. Now we have assumed that these values 1 to n are following uniform distribution. So probability of x being any of these values will be equal to 1 by n, where the value of x is nothing but 1, 2, 3 till n. Now what kind of analysis we can do? We can find the mean or the expected value. So the expected value of x will be nothing but summation for all values of x. That means x is from 1 to n, x into probability, x is equals to x. Now the probability is just a constant 1 by n, so I can take it out of the summation. So this becomes 1 by n summation x, where x is equals to 1 to n. Now before we move forward, there are a few things that you might know but are essential to form these values. First of all, sum of first n natural numbers. If I say summation k, where k is equals to 1 to n, this is nothing but sum of first n natural numbers is equals to n into n plus 1 by 2. You can also find this value by using arithmetic progression. And sum of squares of first n natural numbers is nothing but n into n plus 1 into 2n plus 1 by 6. And similarly, sum of cubes of first n natural numbers is n into n plus 1 by 2 the whole square. So these are the three values that might be required in our further calculation. We definitely require these two. This maybe. So here this is nothing but sum of first n natural numbers. So I can write it as 1 by n into n plus 1 by 2, or you can say it is nothing but n plus 1 by 2. Now let's assume I have a dice. Now each value of the dice 1 to 6, you might say it is same 1 to 6 values. They are following uniform distribution. We are going to assume that each of the value has the same probability 1 by 6. So if we want to find what is the expected value that we can get from a roll of dice, is going to be 6 plus 1 by 2, that is nothing but 3.5. Now that does not mean that we are going to get 3.5 as a value. There is no value as 3.5 that we can get from a roll of dice. So what does this expected value actually tell us? It tells us, let's say I do the same experiment 1,000 times. I roll the dice 1,000 times. So sometimes I'm going to get a value 1, sometimes 2, sometimes 3, and similarly sometimes 6 and sometimes 5 and so on. But for a large number of experiments, the average value, or if I sum all of these values and divide by the total numbers, the average value from each roll is going to be n plus 1 by 2, or our expected value. So the expected value tells us what value should we expect averagely from each of the roll. Now this is expected value. Let's find variance. To find variance, we need expected value of x square, E of x square. So E of x square is nothing but summation x is equals to 1 to n. We'll have x square, probability x is equals to x. Again, probability is just 1 by n. We get summation x is equals to 1 to n x square. This is again sum of squares of first n natural numbers. We have the formula for that too. So we'll write it as 1 by n into n plus 1 into 2n plus 1 by 6. That is nothing but, I can say, now let's find the variance. Variance of x is nothing but expected value of x square minus expected value of x the whole square. That will be I can take n plus 1 by 2 common from both of these terms, and I am left with 2n plus 1 by 3 minus n plus 1 by 2. And if you cross multiply, you are going to get n minus 1 by 6, or this is nothing but n square minus 1 by 12. So this becomes our variance. Now for the same example of a dice, if my n is 6, I am getting 35 by 12. Now this 35 by 12 signifies a value or the variance of our particular value. So if I take root of it, I am going to get standard deviation of x as nothing but under root 35 by 12. This value signifies averagely the each value that we are going to get from our roll, that is going to be above this particular mean, that was 3.5, or below 3.5. That is again an average value. So it gives us a range that we can expect our value to be. So again, the analysis of any kind of data is not going to tell you what a future value is going to be. It only can point us that averagely, or you can say for a particular value or next turn, what we can expect. Again, the next turn might be almost impossible to tell, but averagely for let's say 1000 next turns, I can find an average value that would be the expected value, and each value might be above or below this much particular from the mean. Now let's take another example for the values of uniform distribution. Now here we are going to assume that A plus D, A plus 2D, and so on till let's say B minus D and B. These are following uniform distribution. Now, this particular series is nothing but arithmetic progression, where our first term is A, the difference between the term is D, and the last term is B. Now, if I take arithmetic progression A plus D, A plus 2D, and let's say last term is B, then my last term is nothing but A plus n minus 1 times D. Why? Because first term is A, second term we have 1D, third term we have 2D, in fourth term we'll have 3D, and therefore the nth term is going to give me A plus n minus 1D. Now if we are assuming there are total n terms and the last term is B, then B will be equal to A plus n minus 1D. Now the sum of first n terms, or I'll just write it as Sn, of an arithmetic progression is going to be n by 2, 2a plus n minus 1 d, or is also n by 2 a plus b. Now just bear with me and look at these terms. First term is a, last term is b. The addition of first and the last term is a plus b. Second term is a plus d, and second last term is b minus d. The addition of second and the second last term is also a plus b. Third term is a plus 2d, and the third last term is going to be b minus 2d. So again, addition of third and the third last term is also a plus b. Now, out of n number of terms, how many such combinations can we get? We can get n by 2 combinations. So sum of all of such combinations is going to be a plus b into n by 2. So logically also we can get a plus b into n by 2, or you can just replace a plus n minus 1d with b. So let's move forward. Here we'll say probability of x is nothing but 1 by n, where n can be written, or where I can say last term b is equals to a plus n minus 1 d, where n will be nothing but b minus a upon d. So I'll get b minus a upon d plus 1. This minus 1 goes. So we get b minus a upon d plus 1, or you can say it's nothing but b minus a plus d upon d. So we can say probability x is equals to x is nothing but d upon b minus a plus d. We are not definitely going to use this, but let's find expected value. Expected value of x would be again summation of all values of x into probability x is equals to x. So here probability is again a constant. I am going to keep it as 1 by n, and I get sum of x for all values of x. That is nothing but sum of an AP, because all values are nothing but in arithmetic progression. So I can write this as 1 by n into n by 2 into a plus b. So that is nothing but a plus b by 2. It's nothing but average of first and the last term, or you can say if each value is equidistant and also probabilistic or equally likely to occur, then the average has to be nothing but the midpoint, and the midpoint is going to be first plus last divided by 2. Now for this particular example, we do not find variance just because it is going to be very complicated to sum the squares of a plus arithmetic progression. So this is a common question that might be asked in your examination, but they will always ask only up till expected value. They do not go further. Let's go to our second distribution, Bernoulli's distribution, or it is also called as Bernoulli's trial. Now here what we have is, for a particular value of x, we have only two values. One, let's say we call it as success, the other failure. Now we can write them as 1, 0, or you can say success is denoted by 1 and failure is denoted by 0. And also we know that probability of x being success is known, that is, let's say we are assuming here it to be theta. Now this theta can change, and this will be particularly our parameter for a Bernoulli's distribution. Now here we are going to assume that we are going to do only one trial, and we need to find whether we are going to get a success or whether we are going to get a failure, or how likely is it whether we are going to get a success or whether we are going to get a failure. So now probability of x being the failure is going to be 1 minus theta, because there are only two possibilities. So for generalizing this, I can write it as probability x is equals to x, where x can be either 0 or x can be 1, would be nothing but theta raised to x 1 minus theta raised to 1 minus x. When theta is 0, that means we are getting a failure. This becomes theta raised to 0 as 1, 1 minus theta raised to 1, and we get 1 minus theta, that is probability of failure. If we keep x is equals to 1, that is our success, we get theta raised to 1 and 1 minus theta raised to 0, so we get theta. So this is how we generalize the probability of a probability distribution. Now let's find the expected value. So expected value of x is going to be summation for all values of x into probability. X is equals to this particular value x. Now for x is equals to 0, the whole term is going to be 0. So 0. And for x is equals to 1, theta, we'll get probability as theta. So 1 into theta, just theta. And that is nothing but theta. Let's find expected value of x square. That is summation for all values of x square into probability x is equals to x. Again, for 0, this value is going to be 0. For 1, x is equals to 1, we get theta. So again, this is also theta. Let's find the variance. Variance of x is going to be expected value of x square minus expected value of x whole square. That is nothing but theta minus theta square, that is theta into 1 minus theta. Just for an example, a Bernoulli's distribution is similar to a coin toss. Now I have only two possibilities in a coin toss, that is head and tails. I can assume that head is my success, then this Bernoulli's distribution, let's say probability of getting a head is slightly more than half, or for an example, I'll just take probability that my x will be a head, or let's say here success, I'm just going to write it as 1, is let's say 2 by 3. So out of every 3 toss, I am getting 2 times heads and only 1 times tails. So probability of success becomes 2 by 3. Then the expected value of getting a success is going to be theta, or 2 by 3. That is nothing but out of 3 terms, I am going to get heads 2 times. And the variance is nothing but theta into 1 minus theta. Or you can find it out, it will be 2 by 3 into 1 by 3, and that comes out to be 2 by 9, or the standard deviation of x would be nothing but root 2 by 3. Or you can say the possible values or possible range is going to be of expected, it will be root 2 by 3 above the expected value, or root 2 by 3 below the expected value. Now if you assume this value, let's say it is root 2 is nothing but 1.414, let's assume it to be 1.5 by 3 is going to be 0.5, around 0.5 above our particular value, that is theta, and 0.5 below our particular value, less than 0.5 of course. Next, let's see binomial distribution. In binomial distribution, we write x follows bin, this is just a short form for binomial distribution, with n comma theta, where n is nothing but number of Bernoulli's trial, or I'll just write here number of trials, and theta is nothing but probability of success, and x is nothing but number of successes that we need to find, or you can say we need to find probability for these number of successes. So here what we are doing is we are doing n number of Bernoulli's trial, like I am tossing the coin n number of times, and probability of getting a success, like probability of getting a heads, is nothing but theta. Now we are finding how many number of successes I can get out of these n number of trials. So our possible values of x, the minimum number of successes that I can get out of n number of trials would be 0. I can get all failures, I can get all tails. So basically the minimum value is going to be 0 or 1 or 2, or the maximum number of successes that I can get out of n trials should be n. So the possible values of x would be from 0 to n. Now let's assume that I am doing a coin toss 5 times. And out of these 5 times, I want to know what is the probability that I am going to get success 3 times. So I can get success, 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 failure, failure, or I can get failure, success, failure, success, success, or success, failure, success, failure, success, and so on. I can get many different ways. I can get 3 successes and 2 failures out of these 5 trials, or you can say 3 heads and 2 tails out of 5 coin tosses. So basically, how many such ways I can actually get 3 successes out of 5 trials? So that is 5C3. So we can get 3 successes out of 5 trials using 5C3. Now when I am saying probability x is equals to x, that means I am getting x successes out of n number of trials. So total number of ways I can do that would be NCX. So I am getting x number of successes out of n number of trials. Then I'll take those probabilities and I'll just multiply them, because those probabilities, these n trials, we are assuming that they are independent of each other. So basically, probability of first being success is theta, probability of second being success is theta, similarly probability of this being failure is 1 minus theta. So x number of successes will have theta raised to x multiplied, and we'll have n minus x failures. So out of n number of trials, probability that I am going to get x number of successes is going to be nothing but ncx theta raised to x 1 minus theta raised to n minus x, where our x can be anywhere between 0 to n. Let's find the expected value. So the expected value of successes that we can get using Bernoulli's distribution. So our expected value is nothing but summation for all values of x into probability x is equals to x. Now the basic mathematics to solve this is not very difficult, but it is a little bit complicated, but because it requires ncx. So it is not basically into our course. So we'll use logic to solve this particular term. I said that one particular Bernoulli distribution or Bernoulli trial had expected value as theta. Here what we are doing is we are doing n number of Bernoulli's distribution or Bernoulli's trials. So for one, the expected value was theta. For the second, the expected value will be theta. For the third, the expected value will be theta, and so on. So if we are doing n number of trials, the expected value of n number of Bernoulli's trials should be n theta. Similarly, the variance of x should be n into theta into 1 minus theta, because the variance of Bernoulli's trial was nothing but theta into 1 minus theta. So n number of Bernoulli's trials will give us variance as n theta into 1 minus theta. Just for an example, if I say that for one particular trial I have values, I can get a value between -5 to 5. That becomes my range, -5 to 5. Now if I am doing two same experiments, what is the minimum value that I can get? Now for one I had -5. For two I should have -5 plus -5. That gives me -10. So the minimum value becomes -10 and the maximum value is going to be 5 plus 5. That gives me maximum value as 10. So my range is now doubled. Similarly, if I have three such experiments, the minimum value will become 15, -15, and the maximum value becomes +15. So the range has now tripled, and so on. Similarly, the variance is going to be n times theta into 1 minus theta. That shows us the range of our possible values. So a binomial distribution is formed, or we write it as x follows binomial distribution with n theta. These are its parameters. We can change these parameters to fit different kinds of data. Like the example we took as 5 coins, in which we are getting 3 heads and 2 tails. So we are finding probability that x is equals to 3. That would be 5c3 theta raised to 3 1 minus theta raised to 2. Let's start with the next distribution, geometric distribution. Now there are two types for geometric distribution, geometric type 1 and type 2. Now before we actually start geometric distribution, we are going to talk about geometric progressions and arithmetic geometric progressions, or GP and AGP. Okay, so first let's see GP, geometric progression. Now in geometric progression, we have values as A, AR, AR square till AR raised to n minus 1. Now each consecutive value has the same ratio, or you can say if we divide each consecutive value, we get the same value. So basically second divided by first will be R, third divided by second will be R, and so on. The sum of an geometric progression, or Sn, sum of n terms of a geometric progression, is equals to A into 1 minus R raised to n upon 1 minus R for R less than 1, and we have A 1 minus, we have a r raised to n minus 1 upon r minus 1 for r greater than 1, and for r equal to 1 we'll have first term as a, second term also as a, third term as a, as well as the last term also a. So we have n terms, so I can say it is n times a. Now if you see, the first term and the second term is basically the same thing. If you take minus 1 common from the denominator as well as minus 1 common from the numerator, you get the above value. So I would suggest to remember only 1, that is r not equal to 1. Now similarly, if you have an infinite geometric progression S infinity, we can find the sum of an infinite value also, and that is nothing but a by 1 minus r, where r will be less than 1. First of all, our ratio has to be less than 1. For greater than 1, we cannot find infinite GP, or you can say if we sum, what will happen is we are going to get an infinite value. So this gives us a limited value or a non-infinite value. So simply if you see this particular term, here if we assume r is less than 1, let's assume half. What is square of half? 1 by 4. Cube would be 1 by 8. Fourth power will be 1 by 16, and then 1 by 32, and so on. As we increase the power, we are actually getting this particular value smaller and smaller and smaller. So for n as infinity, this particular value r raised to n is going to be so small, or you can say almost equal to 0 as compared to this particular value 1. So what we do is we put r raised to n as 0 when n is nothing but infinite. So we get S infinity as a upon 1 minus r, only for r less than 1. Now if you are confused, how can we actually sum infinite terms? So I'll just give you an example. Let's say my hands are 2 meters apart, and every single step I am taking, what I am doing is I am doing this, I am halving this particular distance, or basically I am dividing my distance with half. So first I had 2 meters, then in the next step I'll have half, that would be the 1 meter, then half, that is half meter, then 1/4, then 1/8, then 1/16, then 1/32, and so on. Now even after infinite different steps, I will still have gap between my hands. That means my hand will never meet. But simply if I clap, what I am doing is I am doing the same process. First I am halving the distance every single time, and still my hands meet. Now this is called as a infinite paradox. Basically these are many different paradoxes that basically say the same thing. So we are using infinite step to find a finite value, or we are adding infinite values to find a finite value. So it is nothing but in the first step I covered 1 meter as my distance. In the second I have half meter, I covered half meter as my distance. In the third I have 1/4, then 1/8, and so on. I am going till infinity. So this is nothing but an infinite geometric progression. First term is 1 and the ratio is half. So basically sum of an infinite GP would be first term as 1 and 1 minus half, that would be nothing but, if you solve this you get as 2. So basically the sum of infinite term, or the distances that I covered in infinite step, is 2 meters. So even this particular sum is telling us it is going to take infinite number of steps to reach 2 meters, but that does not mean we are not going to reach this particular value 2 meters. Okay, this is saying that this shows that infinite values are actually possible. So let's move forward. this is our geometric progression, or you can say infinite sum of infinite GP. Now let's talk about arithmetic geometric progression, okay, or we call it as AGP, arithmetic geometric progression. Now for an AGP, let's take an example. First term is 1, second term is 2r, third term is 3r square, fourth term is 4r cube, and so on. Let's say I am talking about infinite arithmetic geometric progression. So this is going forever if I am adding all of these. So here my first term is an arithmetic progression and the second term is geometric progression. This kind of series is called arithmetic geometric progression. Now this is just an example, just because finding a general answer for arithmetic geometric progression is a very lengthy process, and the steps that we take to find is very simple. So what we are going to do is we are going to just solve to find these particular values. So if I assume it to be S, what I am going to do is I am going to multiply by the geometric progression value, that is the ratio R. S multiplying S, so I am going to get 1 into R, then 2R square, then 3R cube, and so on. Now if I subtract these values, I am going to get first 1 as it is. Here I am going to get 1 minus R into S, and here I am left with 1 plus R square plus R cube, and so on. So this is nothing but an infinite GP that will give you value as 1 by 1 minus R, or our S is going to be 1 upon 1 minus R the whole square. So this particular arithmetic geometric progression, or AGP, is going to give us S as 1 upon 1 minus R square. Now let's assume another special series that will be required to actually solve geometric distribution. So I will talk about a special series such that I have first term as 1, second term as 2 square R, third term as 3 square R square, 4 square R cube, and so on. So here basically we have squares of an arithmetic progression and the other term is geometric progression. Now we solve this particular kind of special series the same way we are solving this AGP. Just we do the same step 2 times. So let's find this particular value. So we'll take this as S, we'll multiply by R, and we get and so on. Now we subtract. Here we are going to get 1 minus R times S, and here we have 1 plus, it will be 4 minus 1, 3R, then here we'll get 5R square, here we get 7R cube, and so on. Or next step would be 9R raised to 4, and so on. Now this is nothing but AGP. Our first term is 1, 3, 5, 7, 9. This is an arithmetic progression. And second term is R square, R cube, R raised to 4. This is nothing but geometric progression. So what I am going to do is again multiply it by R. So you'll get R, 1 minus R into S. That is going to be R plus 3R square plus 5R cube plus 7R raised to 4, and so on. Then I'll subtract it. So here I am going to get 1 minus R square S, and this is going to be 1 plus, I'll get 2R plus 2R square plus 2R cube plus 2r raised to 4 and so on. So basically this portion is nothing but a geometric progression with my first term being 2r and the ratio being r. So basically we are going to get 1 minus r whole square as 1 plus the geometric progression is going to be a upon 1 minus r. So this is going to be nothing but 1 plus r upon 1 minus r, or s would be 1 plus r upon 1 minus r whole cube. Now we are going to use both of these values, AGP and the special series, that we are getting this in geometric distribution. So I'll just write down both of these values. Now let's start geometric distribution of type 1. Now first of all, we write it as x follows geometric, and we have only one parameter, that is theta. Now theta, we are going to always use theta as probability of success. And here x is nothing but the number of trial, that is our first success. Now let's assume I am a telecaller and I am selling something on the phone. Now due to my past experience, I may know that how many calls are required to make a particular sale. So let's say every 100 calls I make 3 sales. So theta, probability of success, is going to be 3 by 100 or 0.03. And I want to know what is the probability that among my next 10 calls, or you can say my next 10th call is going to be another sale, or you can say first sale from now when I am counting. So we get that x is equals to 10, okay, or the number of trial that is going to give us our first success. Now let's assume I am saying that my 5th call is my first sale. So if my 5th call is my first sale, then all the other calls were failures. So if x is equals to 5, then my first sale or first success becomes 5th trial, and all the other trials are going to be failures. The number of ways I can arrange this is only one, because s is fixed. So therefore all the others are failures. So there is only one way to basically arrange this particular value. So I'll get probability x is equals to x. That means what is the probability that my xth trial is going to be my first success? I can say that is nothing but 1 minus theta, that means failure, and I have x minus 1 failures, and I have only one success. Now what are the possible values of x? Now how many minimum trials do we need to get one success? We need at least one trial. So our minimum value is going to be 1. We can have one failure then a success. We can have 2 failures then a success, and so on. And what are the maximum possible values or maximum possible values for a trial to get our first success? So it can take infinite number of trials to get our first success. All of them are failures. So the possible values of x or number of trials here can be 1 to infinity to get our first success. Let's find the expected value. So expected value of x, nothing but summation for all values of x, that means x is equals to 1 to infinity, we'll get x into probability x is equals to x. So for x is equals to 1, we'll just get theta, then we'll have 2 into 1 minus theta into theta, then 3 into 1 minus theta square into theta, then 4 into 1 minus theta cube into theta, and so on forever. Now here, just for the sake of writing, I don't want to write 1 minus theta again and again. So what I can do is, I can substitute my 1 minus theta with a value q, okay, just for the writing sake. So here I can take theta common, I'll get theta into 1 plus 2 times q, 3 times q square, 4 times q cube, and so on forever, infinite terms. So this is nothing but arithmetic geometric progression. First term is arithmetic progression, second term is geometric progression, and this is infinite arithmetic geometric progression. We found the sum of infinite arithmetic geometric progression as 1 by 1 minus r square. We can directly use this, and I can write theta into, I am going to get 1 upon 1 minus q, 1 minus q the whole square, just write AGP. Q is nothing but 1 minus theta, so 1 minus theta is just going to be theta, so I'll get theta upon theta square, or 1 by theta. This becomes our expected value of geometric progression, that is 1 by theta. Now just use logic. If probability of getting a sale is very small, or probability of getting a success is very small, so expected value of my first sale, or the number of trial that I'll be able to sell my first sale, the expected value, if theta is very small, has to be very large. So we'll get 1 by theta. If theta is very large, that means possibility or probability of getting a success is very large. So my first sale will be much quicker. So the value, expected value of x is going to be a small value, again 1 by theta. So logically also this holds true. Now let's find expected value of x square. For expected value of x square, we'll have summation x is equals to 1 to theta, so 1 to infinity, x square into probability x is equals to x. Now this is nothing but theta plus 2 square 1 minus theta into theta plus 3 square 1 minus theta square into theta, and so on forever. Again, what I am going to do is take 1 minus q as 1 minus theta as q. So I can take theta common here. I get 1 plus 2 square q plus 3 square q square plus next would be 4 square q cube, and so on forever. Again, this is the special series that we just found out. S was nothing but, I'll get what? 1 plus q upon 1 minus q whole cube. Again, q is nothing but 1 minus theta. So you'll get theta into 2 minus theta upon theta cube, or you can say this is nothing but theta into 2 minus theta upon theta square. So what will be our variance? Variance of x is nothing but expected value of x square minus expected value of x, the whole square. That will give us 2 minus theta upon theta square minus 1 by theta square. This is nothing but 1 minus theta upon theta square. This becomes our variance. Now let's talk about geometric distribution type 2. Now in type 2, we write, let's say we have a variable y follows geometric distribution with theta. Now here y is nothing but number of failures before first success. So basically y is nothing but number of failures before we get our first success, and theta here is still probability of success. It is not probability of failure, it is probability of success. Now why do we actually need type 2? Now in the last example, type 1, we had our possible values of x from 1 to infinity. Now let's take an example of a car insurance. Now car insurance, a person studying some car insurance, some policies, is, let's say, is going to study last year out of, let's say, 1,000 policies, how many policies had claims. Now the number of claims is going to follow a discrete distribution. Now the possible values of, or possible car accidents a particular car can have is going to range from 0 to infinity. You can have one accident in January, then after the car is fixed, you can have another accident in February, another accident in March, another accident in April, and every time the car insurance will have to pay out, or you can say depending on the number of times the particular policy allows. But here, let's say we can assume that the possible values or possible number of claims that you can get in a car can be infinite in a particular year. So the maximum value is going to be infinity, but the minimum value, the minimum number of claims that you can have, or minimum number of accidents that a car can have, is going to be 0. So the possible values of, let's say, a distribution of any kind of number of claims has to start from 0 and go up till infinity, or a possible values, possible particular value if it allows so. So because type 1 did not have that particular value, or that was the minimum value was 1, we have type 2 that allows us to get a minimum value as 0. So number of failures before our first success, that becomes y. Now probability that y is equals to a particular value y is going to be, first of all, if I have total y failures and then a success, I have total y plus 1 trials. So I have y failures, 1 minus theta raised to y, and then I have a success, that is nothing but theta. So this becomes probability y is equals to y, where the possible values of y is going to be 0, 1, 2, 3 till infinity. The minimum number of failures that we can have before we get our first success is going to be 0. We have just first trial is our first success, or 1 or 2 till infinity. So this becomes our probability distribution. Now let's find expected value. Now we can use the similar method that we used to find expected value in type 1, but here we'll see a different way. We'll find a relation between type 1 and 2. Now we know our y from type 2. When it was 0, our x in type 1 was 1. When y was 1, we had x as 2. When y was 2, we had x as 3. So I can say y is equals to nothing but x minus 1. So the expected value of y will be nothing but expected value of x minus 1. If you remember, if you have expected value and we have addition or subtraction in middle, we can give individual expected values to both of them, and expected value of a constant is constant itself. So we get e of x minus 1. E of x was nothing but 1 by theta. So 1 by theta minus 1 gives us 1 minus theta upon theta. Okay. So this becomes the expected value of type 2 geometric distribution. Then what about the variance? Variance of y can be written as variance of x minus 1. Variance of a constant is 0. So therefore this becomes variance of x, or it is going to be 1 minus theta upon theta square. So the variance of type 1 and type 2 is going to be same. The expected value of type 2 is going to be 1 minus theta by theta.